that talk is going to be divided into two parts, as I said. This is partly because of logistical reasons. There's a break in the middle. But mostly they are very separate from each other. I hope that from the first part, you take the fact that real stable polynomials are very useful in algorithm design and combinatoric XMA. And from the second part, I hope that you see the connections of these real stable polynomials machinery to the problem of asymmetric TSP. So for the first part, I'm not going to be talking much about asymmetric TSP. That part is going to be that part is the one after the break. So for the first part, I'm going to be talking about real stable polynomials. I'm going to define them in a second. Then I'm going to move on to their connection to probability theory, and especially this notion of strongly Rayleigh measures. Then I'm going to be talking about operations that preserve the property of being strongly Rayleigh, or the property of being real stable. And I'm going to be talking about what these operations mean in the probabilistic setting. Okay, so the first part, real stable polynomials. So this is the slide that we have to be very slow on, because I'm going to be using this definition for the rest of the talk. So let's say we have a multivariate polynomial. It has n variables, and the coefficients can be complex. Okay. I'm going to call it stable if whenever you plug in numbers in the upper half plane of the complex plane, so numbers with positive imaginary parts, you don't get a zero. So people who are familiar with control theory might look at this and realize that this is very closely related to this concept of orbit stability, which implies stability of dynamical systems and whatnot. So that's where the term stability is coming from. But for our purposes, that part is not. So is this clear? This definition. Now, if my polynomial happens to have real coefficients, I call it real stable. So until now, the polynomial could have complex coefficients, but for the rest of the talk, I'm going to be working with polynomials that have real coefficients, and I'm going to be calling them real stable. So if you have a real stable polynomial, upper half plane is the same as lower half plane. Right? If I replace everything in the definition with the lower half plane, I would still get the same set of polynomials. That's because you can conjugate the polynomial's value with the conjugate operator, which just Alright. So for the next few slides, I'm going to be giving you some examples of real stable polynomials. So let's begin with the univariate case. What if my polynomial only has one variable? In that case, real stability is the same as having real roots. It's because it's a very easy observation. Any univariate polynomial has real roots plus some conjugate roots. Right? And if it has a complex root, one of the conjugate pairs has to be in the upper half plane. Okay, that would be contrary to the definition of real stability. So in the univariate case, real stability is the same as being real root. So this is probably the simplest example you can think of multivariate real stable polynomials. So let's say you have a linear polynomial, sum of ai's i's, and ai's are positive real numbers, or non-negative real numbers. Then it's also clear that this is a real stable polynomial because the upper half plane of the complex plane is convex. It's a convex cone. Any positive combination of numbers in the upper half plane would still remain in the upper half plane and would not be zero. Right? Here is a slightly more complicated piece. So if you have two polynomials which are real stable, their product is also real stable. Because real stability was defined in terms of the zeros, right? So if none of them have zeros in the upper half plane, then their product also doesn't have. This one is probably the most important real stable polynomial that people know of. So if you have a determinant of a linear combination of PSD matrices, okay, so A1 through AN are PSD matrices, and you just multiply each one by Zi and then take the determinant. Okay. Then this is going to be real stable. Most of the polynomials most of the real stable polynomials that people care about are either determinantal or are derived from the determinant via operations of preserved real stability. So in some sense, this is the mother of all real stable polynomials. So here's a short proof of why this is true. So let's say that we plug in some Zi's in the upper half plane, and this turns out to be 0. Okay. So you can write the determinant in this way, right? I'm going to separate the real part and the imaginary part. Okay. And then if you factor out this part, the orange part, that's going to be a PSD matrix, right? Because yi's are positive and ai's were PSD to begin with. I'm cheating a little bit because not every PSD matrix is invertible, but let's say that it was a positive definite matrix, not just a positive semi-definite matrix. Okay? If it was a positive definite matrix, you could just factor everything out, and you would get a characteristic polynomial. And the matrix here is symmetric. And you know that the roots of a characteristic polynomial of a symmetric matrix are all real, right? But so t equals I cannot be a real. This basically proves this statement for the case of positive definite matrices. For positive semi-definite matrices, you have to take limits, and you have to use the fact that the limit of real stable polynomials is real stable, which I'm not going to do. Yeah.
Sorry, I didn't follow that argument about the positive definite.
Okay, sure. Yeah. So I'm assuming that this determinant is zero, right? And I'm separating the real part and the imaginary part. Now I'm claiming that this orange part is a positive definite matrix, right? So it's invertible, right? Now I'm going to take it out of the determinant by multiplying its inverse square root from both sides. Then what remains is the characteristic polynomial of a symmetric matrix evaluated at I, which is the square root of negative 1. But I know that the characteristic polynomial has real roots, so it cannot be 0 at I. Okay, so what do the roots of real stable polynomials look like when you look at them in the real plane? So here's an example of a real stable polynomial that we have not seen yet. So if Z1 and Z2 are both in the upper half plane, Z1, Z2 can never be 1. I'll give you 10 seconds to check this. Okay. So this is the canonical. This is one of the interesting polynomials we are going to be working with. So its zeros look like this if you plot them in the real plane, right? Now, there is this equivalent definition for real stability, which we are going to be using sometime later, which works with the roots of the polynomial in the real plane. It doesn't deal with complex numbers at all. Okay. That definition is that if you look at this polynomial at any linear restriction, right? So take P of T times U plus V, where U and V are vectors. Okay. So I'm looking at the values of this polynomial over this line. And I'm assuming that the direction of this line is positive. So U has positive components. Okay. This is going to be a univariate polynomial. Right? The equivalent definition to realizability is that this univariate restriction is real rooted for any pair of U and V. Okay. As you can see, in this simple example that we have, any univariate restriction that we can imagine that goes in the positive direction intersects both this curve and this curve. So you have two roots which are real. Pictorially, that's what it means. There is also this concept of above the roots. Okay. So I think the projector is not showing this very well. But this whole part is supposed to be colored. So that's what I mean by above the roots. So not this part, just this part. So this would be the set of points such that they are the maximum root of these linear restrictions. Take these linear restrictions. I'm fixing a particular direction, which is the all ones direction, but it actually doesn't matter what direction I fix as long as all of the components of the direction are positive. If you look at all of the points above the maximum roots of these linear restrictions, they become this region that I call above the roots. And this region has a lot of properties. In particular, Garding proved that this region is convex. It is upward closed. So if a point is inside and I increase all the components of that point, I'm going to still be inside this region. And this is just saying that the direction that I take doesn't matter. Okay? So for any other vector E, you could have looked at the directions, you could have looked at the linear restrictions in the direction of E, and you would have still gotten the same region.
The fact that they call it negative root is this for this particular polynomial, right? If it was a different polynomial, maybe you should have said positive or?
No, I'm just fixing a direction. You can also define below the roots.
Right.
For real stable polynomials, that region is also going to be convex, but I'm just going to be working with above the roots. Okay.
Is it immediate to see that this region is convex?
I needed to see, sorry?
Is it immediate to see that the region is convex?
No, it's not immediate. It's a non-trivial fact. So let's look at this region in the particular examples of real stable polynomials that we've gone over. So for a univariate real rooted polynomial, this region is just going to be a half line. Right? It's going to be above the maximum root. For a polynomial which is a product of linear terms, this is going to be the intersection of a bunch of half plates defined by these linear terms. For determinant, this is going to be what I call an STP polynomial. Right? So it's the intersection of the STP cone with linear subspace. Okay? So this region would be the set of Z's such that this matrix is bigger than B in a PSD sense. Notice that in the previous slides I didn't talk about these constant terms, but still they work. They would give you real stable polynomials as long as B is symmetric here and these B's here are real.
It's a restriction of these polynomials.
It's a shift of these polynomials.
So if you introduced another variable and fixed that.
Sure. Yeah. Well, I mean, so here B only needs to be symmetric. It doesn't have to be PSD. You could think of it as a shift. So replace zi's by zi plus constants. So there is this Lax conjecture, generalized Lax conjecture, which says that these regions that you're seeing here are no more general than what you get by the determinants. Okay.
So again, by the determinant.
By the determinant, yeah. So the determinant polynomial was giving you a region defined by an STP, right? And generalized Lax conjecture is saying that no matter what real stable polynomial you have, this region is still going to be given to you by one of these. Okay? It's a conjecture, it hasn't been proven. Okay? What has been proven is the special case of two variables. Okay? So when your real stable polynomial has two variables, there is actually something more general that is true, which is that you can actually write the polynomial itself as a determinant. Okay? So the polynomial itself would be plus minus up to signs of the determinant of z1 a1 plus z2 a2 minus b, where a1 and a2 are PSD matrices and b is just symmetry. Okay? So that also implies generalized Lax conjecture in the case of n equals 2. So let's see an example here. So this is our favorite real stable polynomial, 1 minus z1 z2. You can write it as a determinant in this way. So the matrix you get is z1, z2, and 1's on the off diagonal, and the determinant of that is z1, z2 minus. So my initial introduction of the real stable polynomials is finished. Hopefully the next part will be more intuitive. Because I'm going to now study the relation with probability. So far we have been looking at the values of the real stable polynomials. Now we are going to be looking at the coefficients. So first I have to define generating polynomial. Let's say that we have a measure, so a function that assigns to integer vectors with non-negative components, let's say. It assigns to integer vectors positive real numbers, or non-negative real numbers. Okay? And let's say that for now we are dealing with measures whose support is less than infinite, whose support is finite. So these, you can think of these as point processes if you want. So to such a measure, I'm going to assign a polynomial, okay, which is going to be the measure at every one of my integer points times z raised to the power of that integer point. By that I mean zi raised to the power of alpha, the product of that. So each integer point is giving me a monomial. I'm just multiplying that monomial by the measure at that point, and I'm getting this polynomial. Pretty easy. Okay. So if you have a polynomial which has non-negative coefficients, you can also extract a measure from it. Right? So these two are equivalent in some sense. Okay. So here's a measure. Let's say that my measure is assigning a value of 1 to all of these 4 points. Okay. The polynomial I get would be 1 for this point, z1 for this point, z2 for this point, and z1, z2 for this point. Right? That would be the polynomial. I can also factorize it in this way. What is the use of generating polynomials? Well, they're pretty useful in combinatorics because of mostly this property that convolution of measures corresponds to the product of polynomials. Okay. This is basically standard from just the definition. And if you think of measures in terms of random variables, so for a measure, I'm going to assign a random variable which takes the value of alpha with probability that is proportional to the measure at alpha. Okay, so normalize it so that the measure becomes a probability distribution, and that gives you the probability distribution of your random variable. In terms of random variables, this taking the convolution or the product of the generating polynomials translates to taking the sum of independent copies. Okay. So if x is distributed according to mu and y is distributed according to mu, x plus y would be distributed according to the convolution of these measures, or its generating polynomial would be the product of the generating. So let's talk about univariate generating polynomials. So here my measure is just on the positive part of the integers. In general, any polynomial that I get can be factorized in this way with lambda i's which are potentially complex, right? Because if any univariate polynomial can be factorized in this way. Now, what if I require these lambda i's to be real? What if I required my generating polynomial to have real roots? Then you can actually see that for the coefficients of this polynomial to be positive, you have to have lambda i's are positive. That's not true if some of the lambda i's are complex. This is only true if all of the lambda i's are guaranteed to be real. Positivity of coefficients is equivalent to the positivity or the negativity of the roots. So if I require my generating polynomial to be real with that, I can factorize my polynomial in this way and make sure that the lambda i's are positive. And then from this, you conclude that the measure that you were dealing with had to be a Poisson binomial. Okay. Why is that? Because each of these factors, z plus lambda I, is the generating polynomial of a Bernoulli random variable, right? Up to constants, right? You always normalize so that the measure is 1, right? So zi plus lambda I would be a Bernoulli with probability lambda 1 divided by 1 plus lambda 1. Yeah.
Sorry, I got lost a minute ago. Why did you conclude that the lambdas are positive or negative?
Why did I include this?
Yeah.
Because the coefficients of a generating polynomial have to be non-negative. So all I'm saying is that if all of lambda i's are real, and this polynomial has non-negative coefficients, then lambda i's have to be non-negative. Because otherwise, at minus lambda I, your polynomial would be 0, which is not possible with a polynomial whose coefficients are non-negative. So if your generating polynomial has real roots, your distribution has to be the sum of some Bernoulli random variables. This fact is going to be useful later on. And it's also, so it goes both ways. All polynomials, all distributions whose generating polynomial is univariate real rooted correspond to Poisson binomials and vice versa. So here is where I'm giving the definition of strongly Rayleigh measures. So the measure we just saw is not strongly Rayleigh because of a technicality. So I'm gonna require a strongly Rayleigh measure to be supported on 0, 1 to the end. Okay. An equivalent way of saying that is that in the generating polynomial, no variable appears with a power of more than 1. Okay. So the generating polynomial is multiple. Then I'm also going to require that the generating polynomial is real stable, and these two conditions are basically the definition of a strongly Rayleigh measures, which was introduced by this paper. Any questions on what this definition is? So this condition was the one I studied in the previous slide, right? But then for strongly Rayleigh measures, I also require that they are multilinear. So univariate strongly Rayleigh measures are very non-interesting because if you have a multilinear polynomial which is univariate, it's going to be real stable automatically. And the only strongly Rayleigh measures you get here are they just correspond to Bernoulli random numbers. What if you have a linear generating polynomial? So remember that if AIs are positive, this is real stable. Right? What distribution does this correspond to? This distribution corresponds to a measure that takes one of the elements 1 through n with any assigned probability. Okay, so if these are my elements, my distribution is just going to take one of these elements. Each of these elements with arbitrary probability. And it's only going to take one element. So now if I have a product of these linear terms, I have a product distribution. So now my elements are partitioned into these rows, right? And from each row, I'm taking one element. I have a probability distribution over each row, and I'm taking one element from each row. So this is probably the most interesting strongly Rayleigh measure again you're going to encounter. So these would be a subset of these so-called determinantal measures, or determinantal point processes. But for my purposes, this particular subset is going to be enough. And I think you can derive all of the determinantal point processes from this as well. So remember that the determinant real stable polynomial we had. So AIs are PST, and I'm going to also require here that they are rank 1. The reason I'm requiring that they are rank 1 is because I want this polynomial to be multilinear. It's a standard well-known fact that this will be multilinear if these AIs are rank 1. So by the Cauchy-Binet formula, you can rewrite this determinant in terms of subsets of size d of these AIs. So take a subset of size d of the AIs, take the determinant of the sum in that subset, right? The determinant of the sum in that subset would be exactly this term, and sum this over all subsets of size d, where d is the dimension of the spaces. This is just Cauchy-Binet. And if you factorize your AIs as VI transposes, because they're rank 1, there's always such a decomposition, this determinant would be a square, because it's again standard and well known that this is just the determinant square of the vectors themselves. Okay, so this is actually a positive number, or not negative. You could have seen this from AIs being PST as well. So here's the picture. I have these vectors, and I choose a subset of size d of them. So here d is equal to 2. So I choose a subset of size 2, and the probability of choosing that subset of size 2 is going to be proportional to this volume square. So one of the most interesting cases in combinatorics of determinantal point processes is this, spanning tree distributions. Okay? So take these vectors. These vectors are standard in defining the Laplacians on the graphs, and I already talked about that a little bit. So to each edge, you just assign a vector which is 0 at every point, except 2 points at the endpoints of it. And in those entries, it's 1 and negative 1. Right? Then this so-called matrix theory theorem basically asserts that if you take a subset of size n-1 of these vectors, their determinant is either going to be 0 or n, depending on whether that subset is a tree or not. So before you actually ask your questions, I'm cheating a little bit here, because these vectors are always singular. They are always orthogonal to the all ones vector, right? So their determinant can never be anything but 0, right? There are a multitude of ways to fix this problem. You can think of these vectors as living in the space proportional to the all ones, orthogonal to the all ones vector. Okay? So take your favorite linear map that translates that space into Rn minus 1 and apply determinant on that subspace. Or you can also do this trick where whenever you want to compute the determinant of a subset of size n minus 1, you just add a multiple of the all ones vector. So this in particular implies that the uniformly random spanning tree is a determinant of distribution and also a strongly righted distribution. So here's another way you might have seen the matrix 3 theorem. So these vectors, if you take their EEV transposes, these are the matrices that you have to plug into the previous determinantal formula to get the general degree. Okay. In particular, the matrix 3 theorem asserts that if you take a Laplacian of a graph and you compute its determinant in the way that I described, it's going to be n times the number of the spanning trees, which is what you get if you plug in 1 to the generating column. Any questions so far? Alright, so the third part of the talk is about operations that preserve real stability. The most obvious one is value substitution. So if you plug in a real number for one of the variables, you're still going to be real stable. It's actually, you have to do a little bit of work because it's clear that if you plug in some number in the upper half plane, this is going to be real stable. But using limits, you can prove that if you plug in any real number instead of any of the variables, you're still going to be real stable.
Technically, you need something like the fact that the polynomial actually depends on variables other than z1 or something like that, right?
Well, okay, so yeah, that's a technicality. I'm counting identically zero polynomial as a real stable polynomial.
Okay.
For yeah. I prefer, yeah, okay. All right. So what does this do for distributions? So let's say this number c that we are plugging in is going to be 1. Okay. Let's consider that particular case. If you do that to the generating polynomial of distribution, what happens is an operation often known as projection. Okay. So it's like you're just not observing that variable at all. Okay. So in terms of random variables, it's like you previously had a subset. You previously had a vector on 0, 1 to the n. And now you're just taking that subset intersection with two through n. So it doesn't matter whether one is inside or not. Pictorially, this is what happens. These things do get merged with each other. And you get the sum of the distribution. So in particular, for example, this says that if you look at if you have a graph and you pick any subset, such as the edges in a cut, if you look at the probability, if you look at the measure that assigns to each subset x of this cut, the probability that the edges of the cut intersection with the tree are exactly x, that would be a strongly righted distribution. Okay, so you just plug in 1 for all of the edges you don't care about, and you're just taking the projection of the the spanning tree distribution on just these particular edges. There is also this operation called symmetrization, where for two of the variables you plug in a new or an old variable, but you plug in the same variable for both. Okay. So if you do this to the spanning tree distribution, projected on the edges of the cut. So you first project on the edges of the cut, and then you plug in the same variable for all of the z's that are in the cut. Okay. You end up with a univariate polynomial, right? This univariate polynomial, by the facts that we have already seen, is going to be the generating polynomial of a Poisson binomial, right? So this in particular proves that if you look at the number of edges that a tree has in a cut, that's going to be a sum of Bernoulli random variables. That's a very non-obvious fact, and using this machinery you can derive it in 2 lines.
Could you say the last statement one more time?
So take this random variable, the number of edges of a random spanning tree in a particular cut. That is going to be distributed according to a binomial, a Poisson binomial. There is also this operation which is often called an external field. I think that's coming from physics. So if you have lambda i's which are non-negative numbers, if you replace each zi by lambda I zi, then it's still going to be real stable. And this is basically the fact that the upper half plane is closed under scalar multiplication by a algebraic constant. That's what it's saying. So from this, and knowing that the uniform spanning tree distribution is strongly Rayleigh, you can see that the lambda uniform spanning tree distribution is strongly Rayleigh, right? So when you plug in the lambda i's, each spanning tree's probability is multiplied by the product of the lambda i's.
So going back to your first operation where you said if you substitute 1, that's like ignoring a variable.
Yeah.
If you substitute 0, that's like conditioning on that variable not being present.
Sure, yeah, I'm getting to that in a second.
Okay.
Yeah. So there is this slightly more complicated operation called, so take the partial derivative of your polynomial with respect to any variable. Okay. So in the univariate case, if you had a univariate polynomial and you were taking the partial derivative, the fact that if you started with a real rooted polynomial, you would remain real rooted is basically a consequence of Rolle's theorem. Right? That between any two roots of the polynomial, you find the root of the derivative. Right? Okay. So this is basically a generalization of Rolle's theorem to multivariate. If you have a real stable polynomial and you take the partial derivative, you remain real stable. So what does this operation do in terms of distributions? It's basically like conditioning. So when you have a strongly Rayleigh distribution and you apply the partial derivative with respect to, let's say, z1 to it, right? You're throwing away all the terms that do not have z1, right? And all of the terms that have z1 remain unchanged because your polynomial is multiplied, right? So it's like you're conditioning on the first element being inside your set, inside the set that you're selecting. You have to multiply this z1 after you take the partial derivative if you want to get the actual generating polynomial, but that's not very important. You can also get the so here you were conditioning on one being inside the set that you're selecting. You can also condition on one not being inside the set that you're selecting by just plugging in 0 for z1. So this operation throws away the terms that do have z1. So this slide basically proves that conditioning on variables being inside or not inside the set, you still remain strongly Rayleigh. So here is the other cool thing you can do with partial derivatives. So you're selecting a random set according to a strongly Rayleigh measure, right? and you want to know what is the probability of 1 being inside the set. Okay? So you take the partial derivative with respect to z1, and this is giving you the terms that do have z1, right? And you divide it by the generating polynomial itself, and evaluate it at 1. Okay? So this would be exactly the terms that have z1, and this would be all of the terms. So the ratio would give you the probability of 1 being inside the random set that you're choosing. Right? So now if I look at the vector of all of these, this would give me the marginal vectors. The marginals vector. Where entry I is the probability of I being inside the randomly selected set. Okay? You can see that this is the gradient of the log of the generating polynomial, valued at the point 1.
Either you want to speed it up or pause now and then continue now.
I think I have just this slide.
Okay.
Right.
Yeah, another minute.
Okay. So this marginal vector, right? This can only be a convex combination of the support of your distribution, right? Because you're selecting a random subset, and this marginal is just going to be the convex combination of these indicator variables for the subsets inside the support of your distribution. Okay. So I know that this vector is going to be inside this convex hump. And by what Amin just said, you can actually prove that you can always find, so for any point inside this convex hump, you can always find an external field which when applied to your polynomial would give you marginals which are equal to this particular point inside this convex hump you're interested in. Let me go over this slide too. Sorry. So this in particular implies that if you have a KH connected graph by the Nash Williams, which Amin described, you can always find K over 2 disjoint spanning trees. Okay. And if you take the convex combination of these K over 2 disjoint spanning trees, just a uniform convex combination, it's going to be a point which has entries bounded by 2 over K. Right? So this gives you marginals which are bounded by 1 over K. And this is saying that you can always find lambda e's, such that the lambda uniform spanning tree distribution has marginals bounded by 1 over K. Then your graph is K. I'm gonna stop now. I'll do the second part of the talk after the break. Thanks. I have one more slide from the supposed first part of my talk. And this, sorry? Oh. Sorry, I have to turn this on. Alright. So there is this very powerful theorem by Orchia and Brandon, which says basically that given any linear operator on polynomials, you can actually check whether it preserves real stability by testing the stability of a single polynomial. I'm purposefully not saying much on the details, but morally this is just saying that for every linear operator acting on polynomials, you can derive this test polynomial, which would be real stable if and only if t preserves real stability. I'm not going to be using the full power of this. I'm going to be using a special case, which is operators defined in terms of partial derivatives. Okay. So we've already seen that just taking the single partial derivative preserves real stability. Okay. A consequence of this result is basically that if you have a polynomial of the partial derivatives, okay, so partial derivatives raised to powers, multiply together, sum and stuff. This operator would preserve real stability if and only if the polynomial you're applying the polynomial itself looked at as a polynomial is real stable. So, for example, if you are doing this operator, which takes a polynomial and multiplies it by a and adds e times its partial derivative, this would always give you a real stable polynomial if what you started with was real stable. That's because a plus bz is a real stable polynomial. The other example which I like is 1 minus partial squared. You can actually factorize this into 1 minus partial and 1 plus partial. So this is a univariate polynomial which has real roots, if you look at partials as variables. Therefore, this operator also preserves real stability. So next, I'm going to be talking about some applications of the theory of real stable polynomials. This is going to be brief, and in the end, I'm going to get to my main application, which is an extension of Cantor-Singer to strong regarding measures. So strong regarding measures have a lot of negative dependence properties. They have negative correlation. They have basically the strongest form of negative dependence that we know. One of the consequences of this is basically that you can prove concentration inequalities about these measures. So if you have a strongly Rayleigh measure, and let's say that it's supported on sets of size k. Support just consists of sets of size k. Any Lipschitz function of a random variable distributed according to this measure would have Chernoff type concentrations. So it's concentrated around its expectation, and this is the tail probability. So, for example, you can, using this result, you can prove statements like this, which are highly non-trivial if you weren't using this machinery, which is that if you look at the, so this part is not that non-trivial. If you look at the number of edges a tree has in a cut, that would be a function which is Lipschitz. And so you would have concentration. If you look at the number of even degree vertices in a random span tree, that could be useful for TSP, for example. Okay. If you look at this is also a variable which is concentrated around its mean. I've already briefly talked about this. Any univariate projection of a strong Rayleigh measure is going to be a Poisson binomial. Okay? By that I mean if you project it and you just count, so you're counting the intersection of your strong Rayleigh measure with a subset. That count is going to be distributed according to a Poisson binomial, sum of variables. Now, this is very crucial for this paper of mechanics of variance on TSP, the result that I mentioned about improving 3/2 to 3/2 minus epsilon, right, on TSP on metric graphs, on graphic metrics. So in there, they use this lemma, which says if you have a cut, and you know that in expectation, a random spanning tree is going to have 2 edges in that cut, then using concentration inequalities, you can prove things like, okay, it's not going to have more than k edges in this cut with hypo. But you can't prove with concentration inequalities such a statement, that the exact number is going to be 2 with some probability bounded from 0. So this they proved by noting that this is a sum of Bernoulli's and using some machinery that was known about sum of Bernoulli's. So there are these applications which are somewhat remote to what I'm talking about now. But basically, using real stable polynomials, you can get the permanent of matrices. So look at what I'm doing here. So you have a matrix. I'm summing over each row and multiplying that row by a variable specific to the columns. Right? So for each column of the matrix, I have a variable. I multiply aij by zj. I sum them over. This part is linear, right? And if my matrix A has non-negative entries, this is going to be real stable. The product of real stable polynomials is real stable. Right? So this whole matrix on this side is real stable. Right? And this matrix, this polynomial encodes permanent as one of its coefficients, the coefficient of z1 through zn. Okay? Now using this observation, Gurwitz was able to give a very simple proof of the van der Waals conjecture. And he was able to do a lot more with it. He was able to obtain deterministic algorithms for approximating permanent, etc., etc. Recently, we've also been able to use this connection with permanent to apply the machinery of real stable polynomials to problems that economists care about. So Nash filter maximization is the problem we were able to apply it to. But I'm not going to define it here. So the main application, which I'm going to be talking about, is Caddis and Singer. So Marcus, Spillman, and Srivastava solved the Caddis and Singer problem, which I'm going to define in the next few slides. They heavily used this machinery of real stable polynomials. What we did was we extended the result to a setting which was important for our applications in ATS. This statement is going to become clear in a second. But roughly, in terms of graphs, the result of MSS was implying this thing, that if you have a graph that satisfies the conditions they need in your theorem, low effective distance is the things that Amin was talking about, then you can partition this graph into two parts, the edges into two parts, such that the Laplacian on each part is roughly 1/2 the Laplacian of the whole graph. And this technique is the Harvey and Elmer paper that basically proves that if all the effective resistances are small, you have spectrally thin trees. Right? And Amin mentioned that condition is not sufficient for us because KH connected graphs don't automatically satisfy that. So our ultimate goal is to obtain a spectrally thin tree, so we don't need the full generality of this spectral sparsification. We just need the end result to be bounded by alpha times the Laplacian of the graph, and bounded from above by alpha times the Laplacian of the graph, where alpha is the thinness constant. And the Laplacian should be PSD in the space of orthogonal to the always vector. So that's basically just guaranteeing that this is a tree system. So here is the statement that we are going to prove. It takes a little bit of, okay, so it's long, but it's not that hard to understand. So let's say that you have a bunch of rank 1 PSD matrices, A1 through A. You can also write them as in their Cholesky decomposition as the eigenvalue transfers. Okay. Now let's say that you have a stronger Rayleigh measure on 1 through n. Okay. That's supported on sets of size d, where d is the dimension where these vectors are living. So you want to be basically, so this is somewhat selecting a basis out of these vectors. Or at least a set which has the necessary size for being a basis. Okay. Then, with positive probability, there is a set in the support of the distribution such that the sum of the AIs in that set is bounded by epsilon times the sum of all of the AIs. Okay. Given some conditions. Before I go to the conditions, is this clear? Yeah. Somebody say no? Alright. So this is ultimately this set S is ultimately gonna be the spanning tree that we are selecting. These AIs are going to be ultimately the Laplacians on the edges. So on this side, you're just getting the Laplacian of the whole graph. On this side, you're just getting the Laplacian of the tree. Okay. So this is how it's related to spectrally functions. Now, what are the conditions that we need for this? We need small marginals. So each element I should appear in the set S that is distributed according to the distribution you have with probability at most epsilon. Okay. And you want each one of the AIs to also be small with respect to the sum. So if you have an AI which is too large, you might have to end up having to select it, and this won't work, right? So under just these two conditions, you can always select a set like this. The only reason I'm using a distribution in this definition is because I have to look at the marginals. Okay? Otherwise, I could have just given you a support of the distribution. Right? Since this statement is just saying that there is a set in the support. It's not talking about the probability. Alright, so this is how our result compares to what MSS did. So MSS proves a much more general theorem, but their consequence, which is comparable to our result, is for when mu is a product distribution. What do I mean by that? So you have partitioned the set N into D subsets, and from each subset you're just selecting one element. That's what I call the product distribution. So MSS's result basically proves this statement for mu being the product distribution. And we basically extended this to all structured vectors. So this is just some, okay, so recall, these are, Amin has already defined these, but we want thin things. So 3T is thin with respect to the graph G if in every cut you have at most alpha fraction of the graph. Spectral thinness is where this condition is not just satisfied for the cuts, but also for every vector. So in terms of Laplacians, this is the condition you want for spectral thinness. And spectral thinness implies thinness. If you want whenever you're talking about thin trees or spectrally thin trees, what you want is the subset that is selected to just have an edge in every cut. Okay. So here you just want to have an edge in every cut, and here you want the Laplacian to be positive definite on the space orthogonal geometry. So here is what our result translates. So this is a consequence of our result for the scenario of spectrally thin trees. So what our result implies is that if you have a graph and you have a subset of the subset of the edges, F, such that for every edge in F, you have this condition, which is equivalent to the condition that the effective resistance of E is small. So this is equivalent to the effective resistance of E being bounded by 1 over K. Okay. You're taking the effective resistance with respect to the graph G, but the effective resistance is small only for the subset F. Okay. Then our result implies that you can find a spectrally thin tree that is a subset of F. I have to use the fact that F is K edge connected and that these effective resistances are small. So So if your f, if the subset f was the whole graph, this would have been already implied by MSS and RBL. Okay, so the whole new thing is that you can actually constrain yourself to having low effective resistances in a subset. Okay. This is how you derive this from a result. You just let the AIs be the Laplacians of the edges, as I mentioned before. So the strongly Rayleigh distribution that you had to take, remember we wanted a strongly Rayleigh distribution that has small marginals, right? It's going to be the spanning tree distribution on the subset of edges F. Okay? I previously showed in the first part of the talk that if a subset of edges is k-ish connected, you can always take a lambda uniform spanning tree distribution whose marginals are bounded by 1 over k. Right? So that's going to be your strongly Rayleigh distribution. The edges that fall outside of F, they could have high effective resistance, but since your distribution doesn't pick them at all, you actually don't care about them. You can actually break them into parallel edges which have low effective resistance, and you're not going to end up picking them at all in the end, so it doesn't matter. So here is roughly the proof method, and this is heavily inspired by the work of MSS. So we want to show this, right? We want to show that there is a t in the support of our strongly Rayleigh distribution such that the Laplacian of t is, I'm switching my notation to the graph notation because I thought it would be more intuitive, right? So we want the Laplacian of t to be bounded by 1 over k, the Laplacian of our graph. Right? This is equivalent, basically, to showing that there is a set t such that this polynomial, determinant of z times L of g minus L of t, it has no root bigger than c over k. So the max root of this determinant is basically the spectral thinness. That's what I'm playing with. It's not very hard to see. Now, we are going to be working with these mixed polynomials. Okay, so far I want to just point in the support such that this polynomial has no large roots. As in the case of MSS, we are going to be taking expectation of these polynomials, and the expectation is over this subset T, which is distributed according to the given strongly Rayleigh measurement. Right? So this is an expected polynomial, and it's not obvious at all that it has real roots or anything. But we're going to show that it has real roots and that no root of it is bigger than c over k. Then we're going to show that there has to be a point in the support whose max root is bounded by the max root of this average. And then from these two I would get this. And basically I'm going to use the theory of real stable polynomials to get both of these two results. Is that clear? So I'm going to be dealing with this mixed polynomial, the expectation I showed on the previous slide. So I'm taking the expectation of a bunch of polynomials. The expectation is over this variable t. We call this polynomial m. Okay. We're going to be showing that this polynomial is real rooted and that it has no roots bigger than c over k. The way I'm going to show that is basically it crucially relies on this representation, which is not obvious at all. So let me actually tell you what the terms here are. So this m is the polynomial I want to define, I want to get, which is the mixed polynomial. This g mu is the generating polynomial of the strongly Rayleigh distribution u that is given to me. This is the determinant of the sum of the z ELEs. You can also look at this determinant as a generating polynomial of spanning tree distributions, but this spanning tree distribution is not the same as this spanning tree distribution. This spanning tree distribution picks basically any tree in the graph with positive probability, but your mu, the mu here, can pick, won't pick edges that have high effective resistance. Right? This mu is given by some other method, but both of these are basically generating polynomials that span through distributions. I'm going to be applying these operators, which are defined in terms of the partial derivatives. Okay. Remember that I said that polynomial of partial derivatives preserves real stability if and only if it is real stable itself. So this is real stable. Okay. Both of these polynomials are real stable. So in the end, what I get here is going to be real stable. Okay. If I show that this equality holds. In the end, I'm gonna, so this was a multivariate polynomial. I'm gonna plug in, I'm gonna symmetrize all of the variables. So I'm gonna plug in z for all of the variables. And I will, in the end, get this univariate polynomial. Okay. Any questions so far? So notice that if I show this, real rootedness immediately follows. Because all of these operations were preserving real stability, and a univariate real stable polynomial is real rooted.
Sorry, I missed something. How did you get from the bottom to the top?
From here to here?
Yes.
Oh, I haven't shown this yet.
Oh, you guys.
This is going to be, yeah, this equality is what I have to show.
Like if you have that equality, it's not evident at the top. What's the real, you have to explain the relationship. Oh, this relationship is the left side is equal.
Yeah, the left side is equal, or proportional up to constant.
I understand.
So how is real rootedness of this polynomial going to help me out? So fix an edge E in the graph, and think of two distributions, which are the distribution you get by conditioning on E being in T. Remember, T was my random tree that was distributed according to M. So mu1 is the distribution conditioned on the edge E being inside the tree, and mu0 is the distribution you get by conditioning on E not being in the tree. Right? So your actual distribution mu is a convex combination of these two distributions, obviously. Right? And you can actually show that any such combination, so for not just for the theta which gives you mu, but for any other theta between 0 and 1, this combination is going to be strongly valuable. You can basically show that for any other theta, you can get the distribution on the right-hand side by applying an external field to mu. But this is a claim it needs. Now compare this to the mixed polynomials that you get. Okay. Consider the mixed polynomial where the mixture is over the distribution mu1, and m0 be the distribution be the mixed polynomial when the distribution is mu0. Okay. Then the actual mixed polynomial that I have is also a convex combination of these two polynomials. And because of these facts that I've said on the left, you can actually show that if so any convex combination of m0 and m1 would be real rooted if I prove that m of z is real. Okay. Now here's the interesting thing: if you have two univariate polynomials m0 and m1, and any convex combination of them has real roots, then their roots must interlace. What do I mean by that? I mean the kth root of each one is bounded by the k plus first root of the other one. Okay? So these two roots would be above these two roots, would be above these two roots, would be above these two roots. Is the definition clear? And what's more is that if you look at the function that maps theta to max root of this mixed polynomial, this function would be monotonic. So in particular, for the theta you get your actual mixed polynomial m. The max root is going to be sandwiched between the max root of m0 and m1. So this is how interlacing and real rootedness helps me. So it basically proves that either m0 has max root bounded by m, or m1 has max root bounded by m. Okay. And now I can form this recursion tree and do what I was just doing recursively. So remember, to get m0 and m1, you picked an edge, and you conditioned on that edge being inside or outside. Okay. So now you know that one of the two mixed polynomials is going to have max root which is good enough for you. Right? Now you pick another edge, and again you condition on whether that edge is inside the tree or not. And you go down this tree until you reach a leaf. Right? At the leaf, we're going to have an actual single tree. Because you've conditioned on edges being inside the tree. You've conditioned all of the edges. So you know exactly which edges belong to the tree and which edges do not. And because of the way we followed this path, we know that the max root of the polynomial we get at the end is bounded by the max root of this polynomial. So if what we started with had max roots which are bounded by 1 over k or c over k, what you end up with is also going to have max root bounded by c over k. Any questions on this? Okay. So now we have to show that this thing is real rooted, and basically I've already said that this reduces to showing this identity. This is the same identity as before, and I've already shown that this entails that this multivariate polynomial has to be real and stable, and its univariate restriction has to be real rooted. So I've already said that this determinant is also a generating polynomial of the spanning tree distribution, right? So this is the spanning tree distribution where you pick a uniformly random spanning tree from your graph. This mu was a lambda uniform spanning tree, which could also not pick some of the edges. So, okay. So in this mixed polynomial, this determinant, you can actually describe it in terms of this generating polynomial of nu. So if you think of what g nu of z times the all-ones vector minus the indicator vector of a tree T is, if you plug this back into this determinant, you would get from z times 1, you would get the sum of all LDs, which would give you the LG here. And from the minus the indicator of the set T, you would get the minus LT. So this determinant is just this, right? So I'm starting from this mixed polynomial going forward. So this is repeating what I previously said, that mu is a spanning tree distribution, where to each spanning tree you are assigning a probability which could be different from now, this is again expanding whatever I had on the previous slide. I don't know if I should bore you with the details, but what you get at the end is this expression. That the polynomial for a single spanning tree can be written in this format. So you sum over all subsets S. The subset doesn't have to be a tree, it can have any size, doesn't matter. Minus z raised to the power s, and here the coefficient would be the probability that s is inside this random spanning tree U intersection the fixed tree T. Okay. This was for a fixed tree T. I was writing my polynomial for a fixed degree t. Now I have to do a mixture over all t's. Okay. If I do a mixture over all t's, I get this expression here. So the probability of S being a subset of u, the probability of S being a subset of t, times minus z raised to the power of psi x. Notice that this expression I have here is symmetric in terms of nu and mu. Right? And this was not clear at all when we began with the mixed polynomial. So far I've just proved that the mixed polynomial is proportional to this thing. Okay? But this is ultimately what I want. But these two distributions, these two already look very similar to each other already. Right? You have this term, which should probably be coming from here, and you have this, which should be coming from here. And here is what finishes it off. You're applying all of these partial operators, right? From each parenthesis here, you either have to choose one or minus partial derivative squared, right? So let's say S is the subset of the parentheses for which you've selected the partial squared. Okay. Now, if I'm applying partial squared to this product polynomial, one of the partials has to go to this polynomial, and the other partial has to be applied to this other polynomial, because these are all multilinear. So partial squared applied to one of the polynomials would result in 0. Okay? And partial would already give you terms of this one. Okay? So it's not a very big leap of imagination that if you actually expand all of this out, you would get this. Is there any question on this? Yeah. All right. So I've proved this equality. So I've proved this equality. I want to show that the maximum root of this mixed characteristic polynomial is bounded now. Notice that this equality I had was, instead of m of z being equal to this, m of z squared is equal to this. Okay. This is because you get terms from both this side and this side, and you get z squared. So if m of z m of z not having any roots bigger than c over k is equivalent to m of z squared not having any roots bigger than square root of this. Okay. And here is what we want to prove. We want to prove that take the expression that was in the previous slide before applying the symmetrization. Remember at the end I was applying the symmetrization, I was plugging in z for all of the variables. Before applying the symmetrization, this is a multivariate real stable polynomial, and it has a well-defined region above the roots. Okay. What I want to show is that this vector is inside that region. Because when you do the symmetrization, this would become the root of this linear restriction. So ideally, you want to prove such a statement, that if u is above the roots of some polynomial, if you apply one of these 1 minus partial squared operators, then you can move your point u a little bit, so that you still remain above the roots of this new polynomial. If you manage to do this, you can continue inductively by applying the other 1 minus partial squared. And because the direction of your movement is, whenever you're applying this partial, you're only moving in the EF direction, all of these directions would end up being orthogonal to each other, and you would end up at the point t times the all-one spectrum. That would be along the roots. Unfortunately, such a statement, you can't derive such a statement what we can derive is this relaxed notion that if U is well above the roots of multivariate real stable polynomial, then you can shift that point by a little bit in the direction E, so that your point would still remain well above the roots of your polynomial. This notion of being well above the roots is, it's going to be formalized by something that MSS introduced, which is the barrier function. So we've seen this already. For a strongly Rayleigh distribution, this was the vector of the marginals. And I'm defining the infinity norm of this vector to be my notion of being well above the roots. Okay, so at the roots, this thing would actually be infinity, but if as you move away from the roots, this number goes to 0. So what I can in the end prove is that if this value is bounded by alpha, then the movement you need to have is bounded by O of alpha, so that after you do this movement, again the same condition holds, that you are well above the roots by the same measure. Okay, I think I'm running out of time, so I will skip the proof of this fact. But just note that this, because this thing is related to marginals, that's where we use the assumptions of our statement. Remember, the assumptions require the marginals to be small and also the effective resistances to be small. Both of these translate to this thing being initially small. If you do the correct optimization, you get what we wanted, which was square root of C over K. Let's skip this. Okay. So here are the open problems that remain regarding this area. This proof of Caddis and Singer by MSS has found similar proofs for other related interlacing families. I introduced an interlacing family today, which was these mixed polynomials. I showed that they interlace. Okay. Following the path in the interlacing tree, this path in the tree is generally non-algorithmic because for many interesting cases, you can't actually compute these polynomials, these mixed polynomials. Okay? You can actually show that in some interesting cases, these mixed polynomials become matching polynomials, which are hard to compute exactly.
Sharp PR.
Sharp.
Very sad.
So that's the main difficulty of making this machinery algorithmic. So there is a recent result of Cohen, who is, I think, presenting at this conference. Right? So he managed to prove that you can actually compute these polynomials in a setting which gives you Ramanujan graphs of all sizes. Okay, so this is one of the more recent papers of MSS. So in that setting, you can actually compute these polynomials, but we know that this can't be true for all interlacing families. So yeah, that's the main difficulty. And this is more of an open-ended question. Real stable polynomials, I think, are finding more and more applications in combinatorics, probability, and algorithms. So the question is to find more applications. Thanks.